When was the last time you were frustrated while using a computer, or happy or bored with it? In meditation, we're often taught to be an observer of our thoughts and emotions. We repeat the mantra, we are not our body, we are not our thoughts, we are not our emotions. This suits me just fine as I have never been a fan of my emotions. Maybe that's why I like coding so much, because it's so logical and makes sense. Unlike my emotions on the opposite, so irrational and I can't just make sense of them. But are emotions really the opposite of cold logic? I can't help but wonder, is there a way to make logical sense of emotions, such that even computers and AI, which are based on logic and code, could really understand human emotions? And after all, what are emotions for? Why do humans have them? Actually, the problem of detecting and predicting emotions is not a new one. Affective computing has given us many tools for detecting and predicting user emotions. Often, these technologies make use of data from sensory sources like face or heart rate. It works especially well with wearable devices for obvious reasons. But something is missing. It is almost like the sensors only detect my symptoms, but not the cause of why I feel happy or frustrated. With my research, I ask this question, can we mathematically formalize human emotions so that we can explain and predict it without sensory data, based on just observable behaviors and interactive events? To answer the question, we are going to need two things. One, a theory of emotion as a process that we can fully understand. And two, a computational model that can implement this understanding. For the theory of emotion, we're going to use appraisal theory. According to it, emotions are the result of a series of cognitive appraisals that individuals make when things happen. These evaluations are about determining if the event is relevant to one's goal, about how much one can cope with the result of the event or influence its outcome, or how novel or unexpected the event is, for instance. Of the various appraisals in the literature, we chose four: suddenness, goal relevance, conduciveness, and power. I will give you an example to clarify the meaning of these appraisals. My routine after work is to cook dinner, clean the dishes, and watch Netflix. Let's say the routine has been the same for days and I'm feeling bored. Why am I bored? Let's have a look at this appraisal table and investigate. Firstly, as a routine is repetitive, there is nothing sudden in it. So let's appraise that as low. Secondly, this is all of low goal relevance to me, as I have established this routine to save energy for other more goal relevant activities. Conduciveness means whether the event supports my goals or not, and in the case of everyday routines, it is quite neutral. Finally, power asks if I can do something about the situation. Yes, I do. I can of course change my routines as I wish. Okay, now we have a basic understanding of how emotion can be predicted with appraisal theory. Next, we need a computational model to implement it. We decided on reinforcement learning. There are existing models of emotions that use the reward mechanism that drives reinforcement learning. What we did was to take these ideas and combine them with appraisal theory. A reinforcement learning presents a problem about how to optimally navigate a problem. Here is a simple example. Imagine that S1 is a state that describes the start of my evening routine. I always eat dinner first, so let's make an action A1 for doing that. And S2 for me having eaten. I got a reward for eating because I was hungry and the food was good. Next, I need to choose. Do I want to watch Netflix, action A2, or wash the dishes, action A3? The first one gives me entertainment, and I get a positive reward. The second one, well, I don't like washing dishes, so it's a negative reward. Now we can train a reinforcement learning model to solve this choice. In the paper, we provided equations for the four appraisals I just explained. and so we can generate a value for these appraisals from the model in a particular state. For instance, the model evaluates positive power after having dinner because it can choose between Netflix and dishes. We compute all 4 appraisal values, giving us a numerical appraisal vector. This vector can be used to predict emotions using machine learning. In our experiment, we designed 3 scenarios to trigger emotional responses in human participants. The scenarios were designed for happiness, boredom, and irritation. The happiness task was designed to be encouraging and rewarding. The boredom task contained a large number of repetitive tasks and neutral feedback, and the irritation tasks were written with errors and ended up failing the task. The participants would report their emotional experiences at the end, and we use this to check if the model's predictions are human-like. Now, we do not claim that our model explains all there is to emotion, but it did achieve a good fit with human data, meaning our model was able to predict the emotions of human participants in the 3 different tasks. We also designed a second experiment that tested how emotion changes over time when working on longer tasks. Basically, we asked, can we make it bigger? I won't go into details, go check the paper, but yes, we can. The second experiment gives extended evidence that integrating reinforcement learning with appraisal theory is a general way to model emotion. Our approach makes it possible to predict emotions even without any sensors. At this point, I reached a reconciliation with myself. As I have been treating my emotions as devils to get rid of as quickly as possible, I didn't notice the important message they delivered. They are not useless nonsense that pops up just to be of my inconvenience. They are valuable data, show up here with solid reasons to tell me about myself and about the events that have happened to me. Thanks to my research, I can now welcome my emotions warmly and hope you all will also be inspired by this paper.